Hi there, my name is Sam Hirsch. I am a computer engineering student at the University of Utah and a research assistant with Dr. Mary Hall at the School of Computing. So I'm here today to talk about the research that I engaged in over the last semester, which was optimizing C kernel functions with compiler-level transformations. So the goal of this project was primarily to examine the power and the efficacy of these experimental LLVM compiler infrastructure optimization pragmas. These are essentially little instructions that we can give the compiler to have it automatically apply some loop optimizations. So specifically, this work focused on the LU decomposition of a matrix. So if you look at the first figure in my introduction section on the far left of this poster, you can see what the LU decomposition does, which is it splits an original matrix into two triangular matrices, L and U, a lower triangular and upper triangular matrix, such that A, the original matrix, is equal to L times U. It's also important to note that LU factorization can only be applied on square matrices. So any matrices that we used in this experimentation will have the same x and y dimensions. So the methods used, we're applying three different loop transformations, which were loop unrolling, tiling, and reordering. Now, unrolling is essentially taking a single loop. Let's say you have one loop that you go through 100 times, and you do one operation per loop. So rather than doing that, if you unroll that loop with, let's say, a factor of 5, then you would, every iteration, you would do 5 operations, and you would run through that loop 20 times. So at the end, you still have done 100 operations, but by doing this unrolling, you can make better use of instruction-level parallelism, where the CPU is able to execute those instructions at the same time, and decrease the amount of math involved in keeping up with that loop. Next, we applied loop tiling, which changes the memory access order of a loop to make better use of caches. Essentially, the idea is that if you're going to be reusing data, you want to make sure that that data is still in a cache, which is essentially a smaller bit of memory, by the time that you're going to reuse it. If you can have more data that's available in the caches when you reuse it, it's much faster to get that data from the cache than going all the way back to main memory. Finally, we used loop reordering, which changes the memory access direction to make better use of spatial caching. So this is the idea that when you access a piece of memory, you will actually cache memory and some data that is around that memory, around that piece of data as well. So if you can then access that data that is already cached, you can, of course, have more cache hits and, again, make better use of your caches and get a better time. So our results from applying these three transformations showed an impressive level of speed up. So our optimization script focused on 1024 by 1024 size matrices. And if you look at the graph in my results section, you can see that those matrices, our optimized script was able to execute the LU factorization 23.67 times faster than the original code, which is a lot of time saved. Additionally, even though this script was targeting 1024 size matrices, it also worked for other size matrices as well, and we are actually able to get an average optimization of 19.5 times. That is an impressive amount of speed up, especially considering that a speed up factor of 2 times is generally considered very good. So, in conclusion, applying these compiler-level transformations proved to be extremely powerful in creating optimized versions of code. Future work that we propose should expand upon this research by adapting to other machines and developing automatic methods of creating the optimization scripts. So the idea is that these optimizations are highly targeted to the hardware that you're using, so they should be adapted to different pieces of hardware and potentially done automatically without the programmer intervention. Finally, the results of this research should motivate continued efforts to improve LU optimization, these LLVM optimization pragmas, and help them become an accepted compiler standard, since those are only available in development branches, and it would be great to see this become more available to more programmers. Great. Thank you so much. I hope this was interesting.